All right, this video will be a short overview video going over chapter 19, where we talk about free energy and thermodynamics. And we're going to be learning about the three laws of thermodynamics and how they deal with the energy transfer in the universe, the disorder in the universe called entropy. Also, we'll talk about enthalpy and Gibbs free energy. So the first law of thermodynamics states that energy cannot be created or destroyed. This is very important because the universe is at an energy constant. And we always want to consider it like that. And the second law of thermodynamics states that when energy is transferred in any reaction, whether it's a chemical reaction and just an energy transfer, you're always going to have heat that is dissipated into the system and into the surroundings, or out of the system into surroundings. And this is what we call as an energy tax, or better terms, we know this as entropy. Now, entropy is the overall disorder in the universe. And in any what we call spontaneous reaction, which is something that happens without that happens, well, lack of a better word, spontaneously, meaning without any external interference or external forces, we call this spontaneous. And that means the entropy of the universe is increasing for these spontaneous reactions. Now, we have spontaneous and non-spontaneous requires energy to happen. So spontaneity does not mean the speed of it. It just means whether it happens on its own or not. Usually, when chemical reactions are exothermic, a lot of the times they like to be spontaneous because you're going to have energy of the reactants are at a higher energy state than the products, and the release of energy is favorable to the system. But that's not always the case. There are a lot of endothermic reactions that are spontaneous, and it's because of entropy. And we'll talk about that soon. So here's some examples of spontaneous reactions. You have a heavy object from high up. The potential energy is holding it up, but if it were to happen, if it were to go the way that gravity and the universe wanted to in the direction of its spontaneity, it would go down. And chemical changes work in the same way. If you have solid NaCl, it's put into water, the natural spontaneous change will be the dissolution or dissolving. And the same thing happens with diamond into graphite, because it's diamond eventually kind of degrades into graphite because the bonds and the three-dimensional structure of carbon and graphite is more favorable, and it's at a less energy level. So it's spontaneous, but it takes a really, really long time. So the difference between kinetics, we talked about in chapter 15, kinetics, we talked about speed and rates of reaction, whereas in thermodynamics, we only talk about initial and final state, therefore the state functions, because energy is a state function. We only care about the beginning and the end, not exactly how we get there. And there's two types of reactions in terms of energy. We have exothermic and endothermic. And what I said before, and we've seen these in chapter 7, talking about the delta H value, where if the delta H value is negative, that means it is exothermic. If delta H is positive in the enthalpy, that means it is endothermic. And we've seen these before, but now we're going to include spontaneity in there and talk about entropy. Now, most spontaneous processes, like I said before, are exothermic, meaning they go from a higher level of potential energy to a lower level of potential energy, which is more energetically favorable for the system, which I use that term a lot in my lectures, energetically favorable. That just means, let's say if we have two hydrogen atoms, the atoms alone are in a higher energy state than the molecule H2, because that molecule H2, both of its bonded electrons release energy when they become bonded. And this we went over in chapter 9, in chapter 11, with the Vesper model and the bond orbital diagrams, things like that. But that is an exothermic process. And most of these stable covalent bond formations are exothermic. But there are some spontaneous processes that happen and that are endothermic. So how can something absorb energy yet is spontaneous but have a net release of energy into the atmosphere, into the surroundings? So here's an example with melting ice. Melting of ice is an endothermic process, right? Because you have the water particles, the water molecules are gaining energy in order to go from solid to liquid. And we know this, as you go from solid to liquid to gas, the amount of energy increases in the system, in the molecules. So what happens is, because you are increasing the disorder of the once ordered ice molecules to the liquid water, which is now in a more crazy disordered state, what you're doing is you're increasing the entropy. And this is why the process is spontaneous. Whenever you increase entropy of your surroundings or of your molecules or anything involved in the reaction, then you are spontaneous. Increasing entropy is spontaneous. Now, in these exothermic reactions, no duh, of course it is spontaneous, because you are directly releasing energy into the surroundings, and the surrounding entropy will increase. But now you're having the system entropy is increasing, and that also is spontaneous. And another example is water evaporating into gas. That's just the other phase transition. Salt dissolving into water. So here's entropy. What it is a state function that it increases with the number of energetically equivalent ways to arrange components, meaning the more ways of configuring the particles in a system, the more entropy you have, the more entropy those particles have. Processes that increase entropy in the universe are spontaneous. So entropy, more spontaneous. And then we have this equation, which we'll go over in lecture. S equals K natural log of W. K is the Boltzmann constant. And then W is the number of energetically equivalent ways the system can exist. And we'll talk about the way the system can exist when we go over micro and macro states. So that's exactly what we're going to do now. Macrostate is defined by the definitions of the system, meaning the traits of the system, the statistics of the system, the variables, meaning P, V, and T, as an example. The microstate represents the exact distribution of the particles at any one time, meaning where exactly they are. So here's an example. You have blue and red in system A. First microstate, meaning where exactly are blue and red. Red is on top, blue is on the bottom. You could also have a second microstate where blue is on the top, red is on the bottom. Does it matter? No, because the change in energy between both states are exactly the same, meaning the macro state for each one of these is identical, but the microstate is different because the molecules themselves, these particles, are physically in different locations in each microstate. So you can imagine there is a crap ton of microstates, and that's true. For a lot of scenarios, there's a lot. We're going to be talking very simply, but this number W is huge. And you can imagine if entropy, and you can imagine how huge it is, right? Because look at this equation. K is 10 to the negative 23rd. That means the natural log of W, if you want an entropy value in the kilojoules to mole or joules per mole Kelvin, right? You're going to have natural log of W as a huge number, 10 to the 23rd, 10 to the 24th, like that. So these microstate numbers are going to be huge. Now, heat transfer. All right, so we want to talk about this a little bit. So second law, it says that for any spontaneous process, is the best way to sum it up. For any spontaneous process, entropy increases in the universe. But then you can have other scenarios where you're like, all right, when water vapor condenses spontaneously, because it does, right? It goes from a gas to a liquid. What happens? The entropy of those molecules decreases because the gas has higher entropy, more disorder, more randomness. When it goes to liquid, it has less spontaneity, less entropy. Less entropy because it's a liquid. It's a more ordered state. But what did we just talk about? When we go from gas to liquid, we're also releasing a ton of energy. Those gas molecules are now slowing down and forming liquid, getting really close together, making intermolecular forces or intermolecular bonds. And in this process, a lot of energy is being released. So if we come to this bullet point, the entropy increase for these reactions, because in every one of these spontaneous reactions, remember, entropy is increasing. Before, when we went from the melting of ice, right? Or let's say the boiling of water, you're increasing the entropy because the system is becoming more entropic. The molecules themselves are moving around faster, and there's more macrostates and microstates. But if you have the opposite occurring, which is still spontaneous under the right conditions, that entropy increase, because the universe still has an entropy increase, must come from the heat and energy released by the system, and therefore the process must be exothermic. And this is true for most of the exothermic and spontaneous reactions. So here we go, microstate, macrostate, and probability. Now, state A, you have 4 molecule 1, 2, 3, 4 in the left. State B, 1, 2, 3, 4. And then state C, you have 1, 2, 1, 2. Now, one of these states is more probable than the other. And you can imagine A and B are the same because all of the molecules are either on the left, all of the molecules are on the right. So there's one way to do this. If you're talking about which specific molecule is on 1 or is in flask 1 and 2 or A and B. We're not going to use A and B. We use 1 and 2. But for C, you have 1, 2, 3, 4 molecules in different places, and there's different ways that can be arranged. So what we can say is that for that case where you have 2 on the left, 2 on the right, there's only one macrostate, meaning the overall from a kind of from not the perspective of each molecule, just from an overall point of view, there's 2 on the left, 2 on the right, only one way that can happen. But internally, if you were to number, let's say these were little cue balls, right? And you numbered them 1 to 4. There's actually 6 different ways to arrange them. And here are those ways. That means for every macrostate, there are a ton of microstates. And in all of our chemical reactions, it's not just going to be 6. There's going to be 10 to the 50th. There's going to be 10 to the 30th. There's going to be a ton of these microstates. So here's a conceptual question. We'll do that one in class. And the answer is A. Okay, cool. So entropy changes in state change. We kind of talked about this already. In terms of the just overall concept, gases, they're going to have more macrostates than liquids, right? Because you're going to have more disorder and more movement. The molecules are going to be in more places. So the more the molecules move, the more macrostates. And you can see gases have the most. And same with entropy. Going from the hierarchy of solid to liquid to gas, entropy increases as well. Also, so we want to talk about another thing, is that the second law, again, just to reiterate, second law, entropy increases for any spontaneous reaction. Got it. Disorder of the universe increases with every spontaneous reaction. Remember that. But then, oh, we talked about this already. This is the same slides before. Okay. Cut. Remember, the second law demands entropy of the universe will always increase for spontaneous reactions. Entropy increases for spontaneous reactions. Always remember that. But sometimes the increase in entropy is either in the system, and sometimes for exothermic reactions, like we just said, it's the entropy of the surroundings is increasing. But the entropy of the system could even be decreasing as we go from a condensation of water, but that energy released to the surroundings is more. So what this means is that the entropy of the universe is equal to the entropy of the system plus the entropy of the surroundings, right? That makes sense. System plus surroundings equal universe. So in a spontaneous reaction, you have the surroundings, if they are gaining energy in an exothermic reaction, that means the delta S, the entropy of the surroundings, is going to be a lot larger than the entropy lost by the system. And therefore, or not a lot larger, but a little larger, and then the entropy of the universe will increase accordingly. So all we're talking about here is that the entropy of the surroundings, if we have an exothermic process, that means the entropy of the surroundings is increasing, right? Because the energy from the system is being lost, And that energy is increasing the speed of the molecules of the surroundings and therefore the entropy. When we have an endothermic process, the opposite's happening, and we have a decrease in entropy of the surroundings. The point is that if you have a large entropy of the surroundings, that effect is going to be very small, whether that heat release or loss from the surroundings, or the heat gain or loss in the surroundings. So what we can say is that this entropy level in the surroundings is equal to a value, right? It's equal to the heat gained or lost. It's proportional, not equal. And we can say that the change in enthalpy of the surroundings in any chemical reaction equals negative delta H of the system divided by temperature. So it's a very important equation, will be given on the exam. So that's an important equation to go by. So Gibbs free energy, the maximum amount of work energy that can be released to the surroundings by a system. Right there. What that means is when all the chemical bonds break, how much energy is there? So how much energy is associated with all those bonds in the reaction, otherwise known as the chemical potential energy. And this equation is very important. Delta G system equals delta H minus T delta S. That is Gibbs free energy equation. And what we can say is that when delta G is negative, it's spontaneous. When delta G is positive, it's not spontaneous. That's a key thing. And also we could say a lot of other things. We could say delta G will be negative, meaning it's spontaneous, when delta H is negative and delta S is positive, meaning it's exothermic and random. That makes sense. Energy is being released and it creates more enthalpy or entropy. Delta H is negative and large, and delta S is negative but small. So we can say that very exothermic, very easy to happen and very spontaneous. But delta S is negative, but it's very small because of the system it's small, of the surroundings it's going to be large. Delta H, and this is basically saying what cases is delta G negative, meaning spontaneous. When delta H is positive but small, and delta S is positive but large, meaning it's endothermic, but the amount of entropy being given to the system and the amount of because of its spontaneity, the entropy will increase a lot. And the molecules in the system will become a lot faster. And this makes sense at a very high temperature. Delta G will be positive, meaning not spontaneous, when delta H is positive and delta S is negative. So this makes sense because we don't want an endothermic process that loses entropy. If it's endothermic, it has to gain entropy for it to be spontaneous. When delta G is 0, that's what we call equilibrium. So we can say things about equilibrium here. Here comes equilibrium again. So if you have your Q value, which is your reaction quotient, less than K, that means the spontaneity will happen in the forward direction. And when Q is greater than K, that means the spontaneity will happen in the reverse direction. So we can say how spontaneous a certain reaction is forward and reverse. And here's a table showing that. So we have standard states. So standard states, the state of a material in a set of conditions. So for a gas, it's 1 atm. And for solids and liquids, it's usually 25 degrees Celsius. And for solutions, it's 1 molar. So our entropy. So standard molar entropy, or S naught, means that it's 1 mole of a substance at 25 degrees Celsius. And what is its entropy? So here's molar entropies of certain substances, and it's very dependent on the state. So if you look at water as a gas, 188. Water as a liquid, it is 70. Water as a solid, it doesn't show it here, but it's probably going to be less than 70, or it is less than 70. Here are some for liquid and gas of water, like we just said. So you have a standard molar entropy value. And again, if needed, these will be given. And also it depends on molar mass. So it depends on the state. It depends on the molar mass, meaning the larger atoms have more entropy because they have more places for electrons to go and more movement. It also depends on the three-dimensional bonding formation in, let's say, an allotrope. So an allotrope is just a three-dimensional structure, a crystal structure of an element that can form different types of allotropes, meaning like carbon could be graphene, graphite, diamond, and other things as well. So that's an example of an allotrope. And if you have a more molecule or a larger molecule, more molecular complexity, that means you have a higher entropy most likely. So you have carbon monoxide and ethene, both of which have the same molar mass. But since ethene has more atoms and it's kind of physically a little bit larger, then you have a larger entropy. And it's a little bit more complex. So you can arrange those. So standard states and entropy change. It's just products minus reactants. And really, in a lot of this, it comes back to products minus reactants for the Gibbs energy. And these values will be given, and we can do example problems with them. And this equation will be used for that. So if you have a reaction, same thing as delta G system. So you're going to have your delta G equals delta H minus T delta S. And the Gibbs free energy of formation, which is the GF naught, is the change in the free energy when 1 mole is formed. So everything we talked about was standard states. Now we have real reactions. So in a lot of these reactions that happen in real life and not on paper, most of the energy is released as heat into the environment. With batteries, with motors, that's why everything gets hot. With your laptop, whatever, it's hot. Most of the energy is not being used for computational power. It's being dissipated as heat. Now, how can we, this is called a non-standard condition. Now, how do we calculate delta G of a non-standard condition? Well, we can, based on the amount of heat released and based on the reaction quotient. And here's the equation for that. Delta G equals delta G standard condition, meaning the delta G of formation, plus RT natural log of Q, where Q is the reaction quotient. So now we can talk about delta G and K. So if G equals 0 at equilibrium, then we could say the delta G formation equals natural log, or equals negative RT natural log of K, because K is the equilibrium constant. So if K is less than 1, meaning the reactants are more favored, delta G is positive, and the reaction spontaneous in the reversed reaction. So meaning nothing will happen until there's products, which is a lot of the reactions we've seen that only start with reactants. If K is greater than 1, delta G is negative, and the forward reaction is spontaneous. If K equals 0 and delta G equals 0, the reaction is at equilibrium. So here are just some of the equations we have just summed up. And also it could be shown natural log of K equals delta H over R times 1 over T plus delta S over R. So this is in the form of Y equals mx plus B. So what we can say is that the graph of natural log of K versus 1 over time is a straight line with the slope delta H over R and a y-intercept of delta S over R. Again, that information, if needed, will be given to you on the exam. This is just a very brief overview. Thank you for watching. Please like and subscribe.